I'm Maurizio. I work for the compiler team in Oracle, and this talk today is going to be about minimal value types. I like to think of minimal value types as an intermediate point in our journey called Valhalla. And logistically, there are going to be two talks about minimal value types. One is the one I'm doing today, which is more about the origins of minimal value types, where did they come from, and what the programming model looks like. Then there's going to be another talk on Wednesday by Frederick and Bjorn, and this is a much deeper talk in the sense that it's going to explore what it means to add value types in Hotspot and in J9. So what it means to add value type support in an existing VM. So as usual, we're going to need a word from our sponsors, because that's. But please don't rush and buy Oracle products based on the awesome contents of the slides. And as I was saying, I think of this as a journey. We started 3 years ago. The goal was adding value types to the Java language. And we did this for two reasons, or at least we were exploring the space for two reasons. One was to allow the VM to efficiently allocate data structures in a way that was free of indirection, so to achieve flatness and more denseness and density. And also to remove one of the nastiest seams in the language, which is basically the distinction between primitive types and reference types. So by adding values, our dream is to unify references with primitives. And the motto for value types is it codes as a class and works as an int, which is a good motto, but it also gives us some understanding of how things should work when you start using values. So I stole this from Brian's slides from last year. So that's what the object layout looks like today. Of course, you're familiar with it. So if you have a POJO, like a class point with two fields, and you want to create an array, and then you store 4 points inside the array, you get an header for the array, and then each element of the array is going to point to a different location in the Java heap. And in each location, there will be another object with its own header. So the problem with this layout is that locality-wise is not great. The objects are going to be spread all over the heap, and it's very likely that your array is not going to fit a processor or cache line. So if you try to traverse the elements of the array, performance is going to hurt. The layout we want with Valhalla, and we hope to achieve that by simply adding the value keyword on top of the class point, is to have basically an array with all the x and y coordinates nicely flattened inside the same object. So a single header and all the coordinates in place. Why do we have all these pointers and all this indirection? Well, it's a little bit of a tricky question that I'll try to answer as best as I can in this slide. The root of all the problems is caused by object identity. And the meaning of identity, it comes from a Latin word, identitas. Identity is a concept that defines basically what defines what an entity is and what it means for an entity to be what it is. And if you think about cars, like everybody likes cars, we can have two cars, same brand, same make, same colors, same license numbers, but I can still see them as two different cars. I can reason them as being two different things. And the same is true for objects in Java. So I can have two objects, they can have the same values in the fields, they can appear equals, but I can still have ways to poke at them and reveal the fact that they are different objects. How is object identity implemented in a VM? Well, using memory addresses, which means two objects are the same if they are stored in the same memory spot. And since we are using addresses to encode identity, that means that, well, we are basically back to pointers and indirections. Of course, the just-in-time compiler can sometimes help us. It can remove the indirection, it can remove the heap allocation, but only if it can prove that we are not using identity outside the inlining context we are in. So there's some escape analysis going on in the so-called scalarization optimization. And if everything goes well, you don't get any heap allocation at all, and the GC is just fine. But if you are using identity, or the JIT suspects you may be using identity in some other place, then you're not good, and your performance is gonna be bad. So the big question here is, what if I don't need identity? What if I program in such a way that identity is not needed? And speaking about not needing identity, in JDK8 we added this concept of value-based classes. So there are some classes we say in JDK8, like optional, local date time, which are simple data carrier. And these classes are simple, and they are meant to be used in a simple way. So you shouldn't rely on identity when operating on those classes. You shouldn't lock or notify on such classes. You shouldn't rely on reference equality. And these restrictions are meant to be used as a way for us to say, well, maybe today they look like ordinary classes, but maybe tomorrow we can start handling them in a more efficient fashion. And that's basically our ramping up the story for value types, because essentially this is what value types are. Value types are just a glorified version of value-based classes. Value-based class is just a documentation contract. It doesn't mean anything. The VM cannot just optimize based on that. But if we introduce a new construct, which is basically a restricted subset of all the things we basically leave out all the things we don't want from regular classes, and we get to a core which the VM can then optimize efficiently and reliably, then we get to a very good place. The problem with identity is that it's like one of those invasive species. So it's a very handy hook on which to hang all sorts of internal state. GC bits, runtime class of an object, locking information, and what's not. So if we drop out identity, or if we give people freedom to opt out of identity, guess what? A lot of things will not work anymore. Polymorphism is gonna suffer, nullability is gonna suffer. You can't have mutability, of course, because basically identity is essentially there to support mutability in a way. So we are going to lose all these other features as well. But we have a good programming model that we think is gonna give us decent performances. And that's kind of how we approach this problem. We have this mighty beast that we are trying to slay, and we think good value types are going to provide us the sword that may slay the beast once and for all. Well, reality turns out to be a little bit more complex, as we shall see in the next few slides. The first problem you encounter when you add values on top of the Java language is a problem of top types. So in Java, every reference type has a top type, Java lang object, and you can pass references around when an object is expected, no problem. What about primitives? Primitives don't have a top type, right? And by extension, since values works as an int, values don't have a top type either. So how do I write code that works on both references and values? And the trick here is that, well, I could use object, but then I will introduce boxing. So I want to be able to express a routine that works on anything without boxing. That's the challenge. And I may also want to express a routine that works on any value without references, and also on some subset of values, so maybe only the values that are comparable. So we think a solution is going to be to allow values implement interfaces. As I said in the previous slide, values are not allowed to subclass, but with interfaces we could kind of make up for it, and we can have a story for providing and injecting these top types in the object hierarchy. So we could have maybe an interface on top of object, and we could have an interface on top of all the values. The problem then becomes a migration problem, as I will be talking about in a few seconds. How do we reinterpret all the existing code that is expressed in terms of objects to work in terms of this new top type? And that's a big challenge. Generics is another big challenge. Generics are implemented in terms of erasure, which means all the type information is basically thrown away during compilation. So when the VM gets at loading a class, doesn't know anything about generics at all. That works fine. It actually, if you're working on references, it's actually nice because you get a lot of code sharing. But with primitives, again, we are in a bad spot because there's no way for you to share the same representation that works for a string to make it work for a primitive type such as int. Okay, yes, you can work on a list of integer if you wanted to store ints, but as I write in the slide, the primitives plus generics equal boxing. Basically, to store this int inside a list of integer, you need to box it on the way in, because the underlying array, if you have an array list, is going to be an object array. So there's no way around it. You need to box on the way in and unbox on the way out. With values, they work as an int. Again, you will get the same issues. So values and generics don't play well together. We think a solution is going to be generic specialization. So having different runtime representation for primitive, list of int, and reference parameterization such as list of string. Of course, type specialization is a problem worth its own talk. I'm only going to touch upon a few problems in this slide. The first problem is that you're going to need a complete bytecode overall because, well, generics are not expressed in the bytecode today. So we need a way to encode type information, generic type information in the constant pool in some form because the VM is going to need to inspect that. There are also a lot of bytecode asymmetries. If you think about that, the opcodes are dependent, a lot of opcodes depend on the carrier types that you're operating on, and certain operations, such as comparison, are expressed in different ways depending on which carrier you're operating on. And that's going to hurt big time if you want to reuse the same class across primitives and references. Another problem is that we will have specialized type variables, and it is very likely that specialized type variables are going to have their own set of opcodes. So those will need to be added to, for example, to do comparison. Then there's all the language side of the problem, which is how do we express the commonality between different specialized lists. So I have a list of int, a list of string. How do I write a method that can take both? Do I use a wildcard here? Yes, we think there's a story, but we are not 100% sure that we can see the light at the end of the tunnel. And as Karen was mentioning earlier, access check becomes a problem as well when you have different runtime classes. Because if I am inside a list of string and I want to access a private field on a list of int, is that allowed? If yes, well, for the VM, they are just two different classes, so how does that work? We think Nestmate is going to give us an answer there. And also statics. We know what a static field is today. A static field is shared across all instances of the same class. But if there are different runtime class for list, what does static mean? Does it mean shared across all the lists or only shared across a list of int? Those are big problems. And I haven't even started talking about migration yet, right? That's our favorite subject. Of course, Java is an existing language. We would like to, for people to be able to to use those features on top of the existing code that they have already written. And that means, for example, if you have a value-based class, you would like to be able to turn that value-based class into a full value type. We think we have a good bytecode trick up our sleeve here. So we could use the Q letter to denote the valueness. So Q, local date time, means the value. L, local date time, could mean the boxed version. So in this way, we can preserve some form of binary compatibility. But the source compatibility part of the story is still problematic because value-based classes are nullable, value types are not. How do we do that? We don't know. Can we specialize existing collections? That would be nice. Everybody would love to be able to write a list of int for real. Well, that of course is problematic, both from my bytecode perspective and from a source perspective, because we already have a class file with descriptors like list. What does this descriptor mean in this new specialized word? Does it mean reference list, or does it mean any list? And at the same time, at the source code level, if you have a list, a row list or a list of question mark, what does it mean? Does it mean that if I recompile it, it will change semantics? That would be bad. And API are going to be problematic too, because if you look inside collection, there are a lot of methods that basically rely on the assumption that those collections are working on objects. So the primary example for this is map.get, which basically assumes that you can return a null if there's no mapping for your key. Now, if your map is storing values, no null. So how do you do that? Yeah, well, you will need a signature that says optional. And so we need some way for people to migrate away from bad signatures. And that's how we do that is still an open question. We think we have a few good ideas, but we are still not sure about the answer. So as we can see, it's a complicated process to add value types to the language. And so we think it's basically time for a reality check. We've been exploring this design space for 3 years. I think one thing that I can say is that we are more sure now than ever that the direction of Valhalla is actually the good direction. There is a lot of demand for value types. We have seen Vector API, all the interest around Vector API, Panama, GPU experiments, big data. All these things are asking basically the same question. How do I handle a lot of data without too much GC pressure, essentially? On the other hand, though, adding value types to Java is a lot of work. It basically requires a complete redesign of the platform, from the compiler to the hotspot, runtime compiler optimization, ecosystem, bytecode libraries, and even programming model in a way. So the programmers will have to think in a different way for a certain extent. So it will realistically take several releases for us to get there. So does it mean that we don't do anything in the meantime? Or maybe we do something smaller so that people can get started with this new programming model and they get a feel for it, and maybe they report back about what their experience actually is. So let's go back to 2009. Let's rewind the clock a little bit. Around 2009, there was a big discussion in the 292 expert group for Invokedynamic, and the discussion was revolving around what is the role that Invokedynamic should play in the Java programming language. Should there be support for Invokedynamic in Java or not? And I know that Remy was a strong supporter of I want Invokedynamic in Java, of that camp. And one idea that I remember vividly from that time was basically a proposal to add a fake interface called Invokedynamic, without too much fantasy, if you will. And whenever you called a method on this fake interface, Java-C will say, no, you don't really want to call a method on this interface. What you want is an Invokedynamic. I will generate the Invokedynamic for you with a particular name and those arguments. And that was fine for a prototype, really. But it had two problems. One is that it was a stylistic problem, really. It was using the generic syntax to encode the return type of the Invokedynamic. And it kind of gave the false impression that you had primitives in generics, even though you didn't. The second problem, which was far more serious, was that as soon as we added static arguments in an Invokedynamic call side, then the Java syntax fell apart, right? There's no way for you to encode two different argument lists in the same method call in Java. So, okay, scratch that. We abandoned the approach. And we said, okay, what about we make Invokedynamic a VM-only feature? Maybe Java developers don't care at all about Invokedynamic, or maybe they do, but not as badly as VM developers. And in fact, I think we were right, because that gave immediately something to play with for people like Charlie that wanted to write a better JRuby runtime. And it also gave us a way to implement better runtime support for Lambdas in JDK8, Nashorn. A lot of things started because of that decision. And in Insight, it was the right call to make at the time. That doesn't mean that we don't care about Java. As we've seen this morning, we have plans to add Invokedynamic to Java, but not just at that particular time. We did make some few cosmetic changes to the language, so we had the support for the polymorphic signature methods, but since those methods are not really, you can define them outside the JDK, so most people didn't really care about those or didn't even notice that we were making those changes. So in retrospect, I think decoupling the VM changes from the language changes was a winning move. So can we learn something from it? And I think we can. And that's the idea that John had last year after repeated requests from Doug Lee asking for some kind of support for value types. The goal is basically to double down on the approach. Let's change the VM first and let's have the language follow later. But okay, if I want the values in the VM but I can declare them in the language, how the heck am I supposed to even create a value? So the idea is that we let the VM derive a value type from an existing ordinary Java class declaration. So you write your POJO, which is very similar to the one I showed you before, and when the VM loads it, it will magically generate a value type for you. Okay, but then you have to operate on these values. And how do you do that if you don't have language support? Well, two ways, both indirect. One is to spin bytecode, because the VM will provide you extra bytecode to operate on values. And the second is to use method handles. And that's really all there is to it. So just to make a comparison of what the different programming models are here, in Valhalla, when you have a value class, the source for a value class, which is denoted as VC here, you compile it with the Valhalla compiler, and you get a class file for that value declaration. Then when the VM loads it, it gets the runtime class for that particular value declaration. With minimal value types, the picture is a little bit more convoluted. So you start with the VCC, which means value capable class. That's the terminology we're using. You compile it with a vanilla Java compiler, so you don't require any language modification. You just compile it, you get a class file. But since there's an annotation on that value capable class, you know what? The VM will load it. By the time it will load that class file, it will also spin this magic derived value class for us. And that's really the interesting part of MVT. Of course, I'm not here to propose that this is the language I want people to write in 10 years from now. This is just an intermediate step in the road that basically should lead us to Valhalla and full value types in the programming language. So this is just everything that you see in the following slide is going to be temporary and mostly a mean for people to get started with values. So here's how you declare a value-capable class. As you can see, it's a very simple POJO, a class point, two fields, X and Y. And the important thing is that you must put some annotation. The annotation is called value-capable class because, well, it's a value-capable class. And there are some restrictions on value-capable classes which are similar to the one we have seen for value-based classes, so they should be final. The fields must be final. Other than that, they are just regular classes, so they can have constructors and they can have methods. The restrictions are not actually enforced by the compiler because there's no compiler, there's no language change. But in the Valhalla prototype, as we shall see later, there are some options that you can turn on in order to tell the compiler to actually verify those restrictions so that you don't get in bad places. When the VM loads the value-capable class, it will spin something like this. A new class file. You can see its name is $value. The name is not specified anywhere. It could be anything. And the important thing, the first important thing to notice here is that the minor version is set to 1. And this is really what tells the VM to basically unleash all the value type magic so that we can start using the new opcodes, the new constant pool entry mangling, and all that's associated with values. In fact, as you see here, this class has been marked with ACC value to say that this is actually a true value. There is a supertype that has been injected by the VM. It's a supertype that is common to all values. It's something that is a little bit of a knack at the moment. It is handy for the interpreter. It's not terribly important, and it's actually outside the spec, I think, at the moment. And as you can see, one magic thing happened here. There's only fields here, which means the right value is really just a struct. You have only fields in there. All the constructors and the methods have been dropped by the VM. This will lead to some limitation that we shall see. And then you can also notice that there's some name mangling going on. So this class field of the bytecode is pointing to something that says semicolon q point $value. And this is basically required because the verifier needs to know whether it's operating on an entry that contains a value versus an entry that contains just a plain reference class. And speaking about class info have quite a bit of overloading going on at the moment because they are used both to represent class files and to represent types. So for example, if you take the inner classes attribute, the class info in there is used to denote a lexically enclosing notion which is pertain to class files. But if you look at the instructions such as getField, checkCast, instance of, those instructions all speak about classes in terms of types. This all works well if your class file and types have a one-to-one mapping between them. It's kind of the same as we discussed last year with reflection. But if you start having features that produce multiple runtime representation from a single class file, then you run into a problem because you have an ambiguity. What does your class info mean? Does it mean the box version, the reference version? Does it mean the class file? So longer term, of course, we would like to tease apart those relationships, and we would like to come up with different custom pool entries for representing the class file versus the type. But of course, shorter term, this is minimal value type. The #1 goal is to be pragmatic, so we just resorted to some ACI name mangling scheme. Working with values reminds me of the Plato allegories cave because, well, values belong to the VM world. The user never see them, and to operate on values, well, it has to operate them through shadows, either a method handler or some bytecode spinning, but the interaction is never direct. So if you choose to go down the bytecode way, you get some new opcodes from the VM. Opcode for doing data movement, of course. You need to be able to load, store, return a value. There are some opcodes to do field updates on values. You may ask, what about reading a field? Well, I will get to that later. Then you can construct a value. You can do array access, of course, and then you can do box unbox, and that's very important. You need to be able to go back and forth between the value representation and the reference representation of a value. So on top of new opcodes, you also get some overridden existing opcodes. So getField has been given a new semantic. So if getField is pointing to a value class info entry, to a field reference entry whose owner is a class info that is a value, then it will behave as a value getField. And the same is true for a new array, multi-new array. We maybe plan to support also other operation, but not now. So checkCast maybe makes sense, maybe not. As I said before, Q denotes valueness. So whenever you see a Q, either in a type descriptor or in a class info, that means it's operating on a value. Designing the opcode set for values is not an easy feat because there are a lot of constraints. First of all, there are not many opcode slots left in the VM. Secondly, the code size is important, so different choices in how you express operation is going to affect the size of the code generated by Java-C. Third, if you get too smart and try to reuse existing opcode, you know what? The VM complexity is going to increase, or maybe the verifier complexity is going to increase, and we don't know what we don't want that either. So, as an example, if you have an opcode that already takes a constant pool operand, such as getField, you have basically two choices. You can introduce a new opcode called vgetField to state that it is operating on value, or you can just reuse an existing opcode, such as getField, and exploit the fact that the constant pool entry is going to reveal the difference. And we choose the latter approach so that we could save some opcode bits. If, however, your opcode is not taking any constant pool entry, such as vload, well, a load instruction is problematic. It doesn't have a constant pull entry, so how the heck am I going to extend it? Well, I can, again, either add a new instruction, vload, or I can, and Brian had this great idea, we could have a prefix opcode called typed that will point maybe to some constant pull entry, and it will, as an effect, basically update the type state of the VM so that the following instruction will execute as if I'm operating on a value. So even though the following instruction here is saying a load, since there was a type before, I know that it's going to operate on a value. We think that at the moment, the complexity of the typed instruction is not worth because we are only operating on values. But we think that with features such as specialization, type can come back very handy. Because what we care about with type specialization is to be able to have a single class file that can represent the operation for both primitives and values and references. So having a way to also parameterize the data movement operation seems like an easy fit. So in Java, how do you work with values? Well, the short answer is with method handles. The long answer is that basically you need to retrieve an instance of the value type class. This value type, you should think of it as the equivalent of method handles / method handles.lookup. So it's what gives you a lot of factories for constructing method handles that operate on values. And once you get those method handles, you can combine them using the standard combinator API. And one important thing about the 292 support for minimal value types is that boxing and unboxing adaptation has been added as part of the standard method handle adaptation, which means if you're using an invoke or an invoke with arguments, those boxing and unboxing will be performed by default, by their own type. So you can go back and forth between the value type and the box representation. This is a table that shows you that basically whatever operation you can do at the bytecode level is also available in terms of some method handle in the value type class. So consider the second row, for example, get field. Yes, you have the get field opcode that can operate on a value, but you also have the find getter method handle that you can basically retrieve from the value type class. And there's basically one method handle for each operation that you can think of in the bytecode. Of course, this analogy at some point is going to break up because there are operations that are just too fine-grained to be expressed as method handles, and those are the data movement operation. And conversely, there are operations that are too high level. So if I want to do a full comparison of two values, it makes sense to have a method handle for that, but it doesn't make a lot of sense to have an opcode for expressing that. Or maybe it does, but we don't know that yet. So how do you create a value? To answer that question, I want first us to focus on how do we create objects. So you create objects typically by using the new opcode, and that's gonna create an uninitialized object and to put that on the stack. What I mean by an initialized object? Well, it's just an object, but the verifier keeps track of its state and thinks it's uninitialized. So there's this sticky bit in the verifier that says, oh, I can't really trust this object for now. Then an invoke special happens, the constructor is called, the constructor will do some put field in the middle, will initialize some of the fields of the object, and then the constructor returns, and by the time the constructor returns, the verifier will know, okay, now the object is initialized. There are two problems with this model. One is that this model is based on mutation. So you need a lot of put fields to initialize the contents of an object. But the second and most important problem is that those uninitialized objects can escape the context of the constructor. Java developers are always surprised to find out that uninitialized objects can actually leak outside the constructor, maybe through exceptions. So this is not a model that we'd like to expose for values. For values, what we'd like to have is something more stable, where we start off with what we call a default value, which is really a value of the right width with all zeros inside. That's the default value. And starting with that, you basically update one field at a time. But this update operation is not a mutation-based update. It's an update that takes an existing value, update a field, and gives you a new value with the updated field. And we call this wither. So you start with the default, you apply a bunch of withers, and you end up with your result. And the good thing about this is I haven't used mutability anywhere, and there's no need to track uninitialized things around. So there's no such thing as an uninitialized value anywhere. So I think we've improved the model significantly. How do you create a value? By spinning bytecode. This is what the bytecode actually looks like. So you start off with an opcode vdefault. Vdefault is actually what tells the VM to give you the default value for that particular type, in this case $. Value, which is the derived value class that the VM has generated. Then you store a bunch of coordinates inside the point for x and y with a bunch of v-with field. So v-with field is the opcode that you need to update fields of a value, and then you can v-return. And that's how you do it. If you want to use Java, well, the situation is a little bit more convoluted because you need to use method handles. But it's still manageable. First off, most importantly, you need to retrieve an instance of the value type class. And you can do that starting from the value capable class. So you pass the Javaland class for that, and you obtain a value type. And then you can start asking this value type the method handle for the default value, the withers, and then you can combine them all together to form the factory that you want to get here. So you want a method handle that takes a bunch of coordinates and gives you a point for those coordinates. And you can use just the regular method handle combinator API for this. Lambda forms, that's a tricky problem. As you know, method handles are compiled down to Lambda forms, which is good because it means that different method handles can share the same underlying representation, but the way this is done is through erasure, once again, which means that basically method handles, the signature of Lambda forms don't make any distinction between whether they are operating on an int or on a string versus a runnable. They are all, the same Lambda form can be used. So the question now is, what should we do for value types? Should we erase value types, or should we not when we deal with Lambda forms? If we don't erase value types, then we are back to the original problem with method handles, that basically we have a lot of bytecode spinning going around. But if we do erase value types, what do we erase them to? If we use object, we are basically doing boxing. So we need some other type. And we think that right now, the type we are using right now is the __ value, which is the special super type that all values know about. But this is, of course, an hacky solution. We think a more and better longer-term solution should be to use the so-called universal type that I'm going to talk to you about in a moment. How do you call methods on values? Well, in Valhalla, that's easy. There is an opcode that is called Invokedynamic, which allows you to take a value and call a method on it. This opcode is particularly magic because if you are calling a method that is defining some interface, because it's a default method, it will also do some boxing transparently. But in minimal value types, there's no such thing as a method on a value. As we have seen, the VM will basically prune away all the methods and constructors. So how do you call a method on a value? Well, easy. You box, and then you call the method on the box. It's of course not great, but one good thing about this boxing is that this is not while it still creates a Java object, a regular Java object on the heap, the C2 compiler and the JIT in general is way freer to optimize away this kind of boxing, because it knows that the identity that is being introduced here is completely accidental. So this is how you call a method on a value. You first load the value using vload, then you do vbox, and then you just do an invoke virtual, and that just works. I'm not showing the code with method handles because it's just silly, because with method handles, the vbox happens transparently, so you just need to retrieve the method handle that does the call that you want, you just pass the value, and the boxing will happen. So as we have seen so far, basically boxes, classes, and values are just separate classes in minimal value types. The only thing they have in common is this box and unbox opcode that allows them to go back and forth between one and the other. Longer term, we would like to have a more fluid notion where basically both the box and the value class can be defined as projection of some common entity. And that's an idea that John had about attaching to each type a mode. So we already know about the Q mode, which means a value. We already know about a L mode, which means reference. But there's, we think, also a third interesting mode, which is called U, where U stands for union or universal. It's basically a carrier type, a new carrier type, that basically can be used to store both a value or its box. And the cool thing about a U is that when you store a reference type inside a U, it's a boxing that preserves the identity. So when you get back the reference object, you get back the same identity that you started with. And another cool fact is that when you store a value inside a U, you don't need boxing, because U is big enough to also encode values underneath. So you don't need to allocate an object on the heap. We think that this is going to be a very important instrument for our experiment. First, for Lambda forms, because U is a natural arrays type for values in Lambda forms. And secondly, because it will give us a way to express things such as code that needs to work polymorphically on primitives and references in type specialization. So we think with U types, we have a way to write the method body once and for all, and then to let it run both on primitives and on references. Of course, you can do also more complex code in Valhalla. You can, for example, take an array of points, and maybe you want to compute the sum of all the norms of these points. And if you have values in the language, that's easy. You just write a for loop, or maybe a stream, and a reduce operation, whatever you prefer. But what if you don't have values in the language? Well, this is starting to look ugly, doesn't it? I mean, we can still see what's going on. We need a for loop combinator, and there are many pieces that goes in there, but it took me an hour to put this slide together and make sure that the example actually worked, because there are a lot of types that are just dynamically present. There's no support for, I mean, the compiler doesn't check that what you're writing is actually correct. Maybe spinning bytecode could be a better option when you need to generate more complex code. But at the same time, first you need some good toolchain support for value types. So I asked Remy, please give us some support for ASM for working with values. But secondly, it's still a dynamic approach. So by the time you're writing your code, you have no confidence that this code is verifying or it's even doing what you thought it was doing in the first place. So the lesson here is that minimal value type is a point in our journey, it's not the destination. Of course, the destination is to have a full programming model with values in it, and that will give you all the benefits of having better layout for data structures and also having programmers a better way to express the constraints that they want. MVT is basically a way for us to give you guys something that you can play with and report back some experience on what you think about the value support in the JVM. So speaking about what's there now, so first, well, basically we are looking to ship MVT as an experimental feature, as an experimental VM feature. So we will probably adopt a model which is close to the incubator model described in ZEP 11. So there will be so-called value-capable modules, and the set of value-capable modules can be expanded through a set of JVM incantation flags. There is going to be a spec addendum for value types, and the delivery format for that is still TBD. But we do have a spec. Thanks, Dan, for putting that together. So we do have a full spec for values, and that's a really important piece. And we also do have a prototype that 99% matches what the spec says. There are some differences with the ordering of class loading, but those are all details. the high order bits is that it works, and you can write all the examples that I've shown you in the slides, and they just work, and they actually get good performances too. We had some preliminary benchmark, and the results are looking very interesting so far. The support in this prototype includes full runtime interpreter support, but there's also JIT optimization in place, only for the C2 compiler and only for the Linux x64 platform. There is also support for the method handler runtime, and all the combinators methods have been adapted to also work on value types. And there's also an experimental extension to Java-C that allows you both to generate value types directly, that's useful for testing, and also to enforce extra checks when you declare a value-capable class, if you want to be extra sure that you are actually doing the right things. Of course, I warmly suggest that you go out there, you fetch this, and you try to write whatever stuff you have right now using the MVT and report back on what your experience is. This is kind of the team that I had the pleasure to work with over the last year. As you can see, there's a lot of smart people in here. So it's been an honor for me to work with them. And that's the last slide I have. So thank you for your attention.